All right, in this lesson, we're still going to compare series, compare sequences, but now we're going to use the limit. So let's start by using the comparison test, or trying to use the comparison test on this. And we still start with prediction. Does it look like this will converge or diverge? So we see a linear term in the denominator, so that means we would think it's going to be behaving like the harmonic series, so we think it will diverge. Then we have to choose something to compare it to, and that would be the first guess. Because it looks, overall, it's a 1 over n, so here we have, we're going to compare it to that. And now compare. And we need to show that this is greater than. We want to show that it's greater than. If we think it diverges, then this has to be greater than that. But it's not, because of the this denominator is greater than that. So it is less than, and we can't do this. But the new test is, or the variation is, why don't we just take the limit of the ratio of these two? And so I'll take this in the numerator, and that in the denominator. So the idea here is, even if this is greater than that, but it behaves in the same way, then they are going to approach their limits at the same rate, and that means this will cancel that, and we'll get a constant. The limit will exist if they both do the same thing. So now let's rewrite. Multiplied by the reciprocal. And this is infinity over infinity. That's indeterminate. If it's indeterminate, then we can use L'Hopital's rule, which is just finding the derivative of the numerator and the derivative of the denominator, then reevaluating. So this is the limit comparison test. Because the limit exists, we can say by the limit comparison test. So we are comparing the harmonic series with this series, but we had a problem with direct comparison, so we just find the limit of the ratio of these. If that limit is some number, then it has to be I'll write down the theorem, but if it's a positive number, then they both do the same thing. If the limit exists, it doesn't mean it diverges. It just means that it will do whatever the thing you're comparing it to does. So if this diverges, then this diverges. If this converges, then that converges, if the limit is a positive number. And here's the limit comparison test. If the limit is L, and L is finite and positive, then both the two series of the sequences that you're comparing they both converge or they both diverge. All right, so pause the video and try this one. When we look at the denominator, it's n squared, and 1 over n squared converges, the series of 1 over n squared. So we're going to predict that it converges. Let's choose something to compare it with, and that would be 1 over n squared. If we think this converges, then we have to show that this is less than the sequence of the series that converges. So that's going to be hard to do. Instead of doing that, why don't we do the limit comparison test? The limit as n goes to infinity, and we'll have and when we let n go to infinity, we get infinity over infinity, and that's indeterminate. If you have an indeterminate form, then you can do L'Hopital's rule, and that's just going to be the derivative of the numerator, the derivative of the denominator. If we do here, evaluate at infinity, we still get infinity over infinity. So we can do L'Hopital's rule again, which will give us 2 over 4. And the limit is 2 over 4, 1/2. The limit is a positive number, so we get, so we know they both series do the same thing. Since this converges, this also has to converge. So we say, therefore, all right, here's another one. Pause the video and try this. So we look at the degree of the denominator, and the degree is 1/2. If the degree is 1/2, we think it might diverge because it reminds us of that. And this is a divergent p-series because the power, the exponent, is between 0 and 1. So this diverges, and that means we think this will diverge, and now we just have to compare. We need to show that this is, if we're going to say this is going to diverge, it has to be greater than this. But Looks like it might be less than if you have that 3 in there. So we have to do the limit comparison test. So let's just do a shortcut here. Instead of all that flipping and multiplying, we'll just have this in the numerator. So we just skip some steps. So this divided by this is the same as this multiplied by this reciprocal, and that puts the radical in the numerator. And then we can think of it like this. And we can also think of it like this. This limit is indeterminate because we'll have infinity over infinity. So we can do L'Hopital's rule, which will be a 1 over 3. And that gives us the limit is 1/3. Leave the radical. So we have radical 1/3. The limit is a positive number, so that means that the series that we're testing must do the same thing as the series we're comparing it to. We know that this diverges. That means they both must do the same thing, and that means this series diverges. And we'll stop there.